Hello, my dear audience. Welcome to the video demonstration and the assignment video presentation for our assignment 2 of the machine learning module. Let me first deep dive into the topic that we have selected. Uh, the topic that we have selected is machine learning for breast cancer prediction. I am Praveen Palihena, and with me I have my colleague Supasan. So let me continue. Yes. Going into a introduction about this, the context that we have selected to go through with this assignment. So, without a doubt, cancer is actually a lethal threat to the mankind. So there are many types of cancers. Uh, so among those cancers, the breast cancer remains one of the most prevalent cancers worldwide, which is actually the leading cause of cancer related to deaths of the women. So actually, the earlier detection of these cancer cells is actually a vital thing, because in order to have the proper medication of this uh, patient in the early stage could save her life with proper diagnosis. So through this study, what we are going to do is to have a look at how the ML algorithms that can be used in order to predict the cancer cells beforehand, so that the patient can be directed into proper medication treatments. So yeah, in this study, what we have selected is we have selected two supervised learning algorithms, which is the decision tree and also the support vector machine algorithm. So we actually employed these algorithms in this assignment. So going forward, so actually, according to this study, what we are aiming for is to contribute the valuable insights into machine learning for cancer prediction. So, and also to provide directions for future improvements in critical domain. So yeah. Then let me give a background about the dataset that we have selected for this study. So we have actually gone for a publicly available dataset, which is available in Kaggle. So the dataset that we selected is the breast cancer Wisconsin dataset, which is available in Kaggle. So let me just give a brief about what is actually in that dataset. So this dataset actually contains data derived from digitized images of fine needle aspirate samples of breast masses. So the objective of this data set is actually to identify whether the tumor is a malignant, which stands as bad, and also if it is benign, that is good. So that's the objective of this data set. So this data set actually includes 569 instances in total, and each instance has attributes, that means features of 32. So these 32 features include 30 real valued features, and also then the ID to identify the field, and also what is the diagnosis of that particular instance. So in that, among those 30 real value features also, there are 10 key features. That is, as you can see in the slide, radius, texture, parameter, so area, smoothness, compactness, concavity, concave point, symmetry, and the fractal dimensions. Those 10 key features are there. And also, each feature actually represented as mean and standard error and worst, which is the largest value across the cells. So this is how the consistency of the data sets have been presented during this in this data set. So this is the data set that we selected. So next, so in this data set actually, so there are, as I told you, there are 32 attributes in there. So it's a lot actually. So there can be interdependencies between these, in between some of the features. So that can be lead to a failure of training getting a successful output of the train module. So we have to overcome this issue. So for that, actually, we created a heat map. So in order to identify what are the correlations in between, the interdependencies between the features, and also in order to avoid the potential uh, redundancies in between these features. So we actually created this heat map. So this is the heat map that we have created. So according to this heat map, if the correlation value is near to +1 or -1, that means that has a strong interdependency, and also those interdependencies, and it actually can be a possible redundancy. So if that case, we have to remove those interdependencies, when it comes to the model training, so that we can get the other features into training model and have a better possible outcomes. So yeah, according to that approach, so these are the 9 features that we have identified, which has the strongest correlation to the key variable, which is the diagnosed variable. So these are the 9 variables features that we have identified. So yeah, so going forward, so what is the methodology that we have followed? So this is in here, as the methodology is actually a very structured methodology that we have followed, which is to first go into the data preparation part, then the data modeling part, then the evaluation of the model. So first, so by using this dataset that we have selected, we actually loaded this dataset into separate data frames. So one is containing the feature data, and other one containing the target labels. So this setup actually allows the organized data manipulation, and it's actually easier handling of features and the labels independently. So following this approach, label encoding, this label encoding was applied to the diagnosis column in order to convert the categorical labels into numerical values. So after that, we actually applied data normalization as well into this feature set to ensure the consistency and improve the model performance. So through normalization, actually what we did was to adjust the scales of feature values. So it's actually important here due to the large range of differences among features. So as an example, there are the area, the texture parameters. So those are a large range of values are in here in those features. So by scaling the features into standard range and in normalization, it actually reduces the biases towards the features, which larger scales, and actually the model converges during the training. So that's what we have trying to accomplish during this normalization. So yeah, going forward, actually, these are the 2 approaches that we have selected. One is the decision tree model and support vector machine. So let me pass on the presentation to Supasan to going on with the methodology, how we did during this methodology, and how the outcomes would be of that. Thank you. Yeah, over to you, Supasan.
Thank you so much, Praveen. So as Praveen mentioned, the first approach that we took is decision tree model. So can we move on to the next slide, please? Yes, in the decision tree model, we split our dataset into 70 and 30% ratio, where 70% is used for training and 30% is used for testing. In the training dataset, there's X, all the features that Praveen mentioned, and the Y variable with the case is a malignant. I mean that it is a healthy or unhealthy case. Then, according to our algorithm, we use scikit-learn decision tree model to train the dataset, and after we train the dataset train the model using the training dataset, we use our testing dataset, the remaining 30% to test. So according to those values, we got an initial accuracy of 0.93. Then we take another step to check how the depth of the decision tree is going to affect to the accuracy of the model. So we use the depth values as 1, 2, 3, 5, 7, 9, and 11. And then separately we train and come up with the optimized score of the model. And we draw this graph so we can see the best depth would be 3. So for the testing data and the training data, it always come to the accuracy point because we're using the same data and then again, likewise. So this is the optimization method that we use. And so as a summary, we have 0.93 accuracy in the decision tree model. Moving to the next slide, please. So the next one is we use a support vector machine. In support vector machine, we use 80-20 data ratio, where 80% of data we use training and the remaining 20% we use for testing. So when it comes to 80%, according to our data set, it is 455 points, data points, and the remaining 114 data points we use for testing. And can we move on to the next slide, please? In the support vector machine, we got an accuracy of 0.95 accuracy. And then we came up with the confusion metrics to visualize the model predictions. So at a glance, in the confusion metric, there are 71 true negatives, 0 false positives, 6 false negatives, and 37 true positives. If we take, we have 0 false positives, which means no instances were incorrectly classified as class 1 when they were actually class 0. The class 1 and 0 is the healthy and unhealthiness of the y variable according to the features that we took. So then we use the precision value, where for the class 0, we got 0.92 precision value, and the class 1, we got 1 as our precision value. And then recall is to indicate that model successfully identified all actual class 0 value as the zeros. And when it recall value, when it comes to class 1, it's 0.86, which indicates that the model identified 86% of the actual class 1 instances. And then finally, we took the F1 score, which represent for the class 0, 0.96 is a balanced metric that combines precision and recall of the class 0. And when it comes to class 1, it's 0.93, representing the balanced metric that combines precision and recall. So these are the parameters that we have came up with the SVM model performance. Can we move on to the next slide, please? So as overall, as Praveen mentioned, this is a very critical thing. If we can predict the breast cancers in our early stages, that would be very helpful for all of us. So as a discussion, we have the high accuracy and the robustness in the SVM. And also when it comes to decision tree, we have transparent interpretable approach. So both decision tree and SVM model demonstrate high accuracies and the classifying the breast cancer cases according to the data set that we have used. Can we move on to the next slide, please? So as a future work, so if you can improve this work by identifying the most correlated features and then train the model again to come up with better results. And also we can remove, as Praveen earlier mentioned, all the redundant features, because if one feature is repeatedly doing the same thing, that is also not very efficient. And those are the future work that we saw in our particular study. So these are as a conclusion, we came up with a method using decision tree and SVM classifier, which can support early breast cancer diagnosis. So can we move on to the next slide, please? I think, yes. So thank you very much for our presentation. So this is our work. So let us show a small demonstration about what we have done by running our code using our Python notebook.
You're on mute, Supasan. You're on mute, Supasan.
Yes, I'm sorry. So I hope you can see my screen that we developed uh, our code. So this is the code that we developed. Basically, we use scikit-learn, NumPy, and Seaborn for the outplotting. Uh, these are the libraries that we use, and this is the code that we developed. So let me try run our code. First, we import the dataset using the library that was in the dataset. And this is the summary of our dataset. This is the variables that we discussed. And this is the confusion matrix. And this is how we use our decision tree classifier. And this is how we how to optimize using the different depths of the decision tree. And this is our confusion matrix that we use for the SVM. And this is our precision we call F1 score. So thank you very much for your time. And this is our presentation. Thank you very much.